Okay, welcome back. Very cool. Moving there. Okay, in the previous recording, hey, look, I'm in a new room. I'm in a different. It's a different day. That's also sorted there. Okay. So in the previous recording, I went through with you how to determine and how to define the direction that electric field vector and electric field line points. And remember, I said that the choice has been made to define the direction of the electric field to be the same direction that the electric force that field would cause on a positive test charge if you would put a positive test charge in the field. And so at every point in space, remember the field exists at every point in space, if you were to place a positive test charge somewhere in space and release it, it would experience an electric force, and you know that because it accelerates. Whatever direction that force points, the electric field is defined to point in that direction. Please keep in mind that part of the definition is that the test charge that you place wherever in the field is going positive. Not that you can't put negative charge in the field, of course you can. What I'm saying is that the direction of the field is defined by the direction of the force that was applied on a positive charge. So if you put a negative charge in the field, then the field would point, let us suppose, that way. If so, then the force on a negative charge in that field at that location, the force on a negative charge would point the opposite direction. Okay? So if I have a field and if I put a proton here and it accelerated that way, if I then put an electron here at the same place, it would accelerate that way, exactly the opposite direction. But the field is defined to point that way because that's the direction of the force in a positive charge. So there, again, for the definition of the direction of the field, there are no test charges for that. It's simply a concept. What if I did put a positive charge? If the force on it would point that way, then we define the electric field to also be pointing that way, at that location. Okay, so that's much for that. What I said at the end of the previous recording is that there's some rules that you have to follow when you're constructing an electric field line diagram. Okay? And I want to go over this with you because the purpose of an electric field line diagram is to just try to help you wrap your head around what the field looks like, and sort of try to picture it. And if you want to do that, then it's important to be able to draw the field correctly so that you're picturing the correct thing. So the rules are not onerous, and they're not difficult, but not very many of them, but let's go through them. So I'm going to start with the simplest non-trivial chart configuration that I can come up with, and that's the field of the dipole, which is nice. We've seen it a few times. Starting to get comfortable with it, I hope. But it has enough complications with my features that I can usually talk about that. As I do this, please keep in mind that even though I'm trained, of course, to draw a two-dimensional surface that I've said several times now, the electric field, the physical phenomenon, is three-dimensional. It exists out in space in front and behind the chalkboard itself. So here's our dipole, and I'm not going to be using colors as much here because I'm on a chalkboard and colors are a little more difficult for you to see on the video. I may do some, so I'll try to make it clear. Okay, so there's the dipole. We've already talked about what the field looks like, but I want to take a step back in constructing the rules that I want to give you and think about a little more systematically how we construct the electric field. And I already said this a little bit, but I want to step you through it a little more carefully. And so I said, okay, if, for example, let's keep a random spot somewhere, and we see the spot sort of close to the positive charge. Now, if I were to put a positive test charge at this point, then of course it would be repelled by the positive charge, it would be attracted to the negative charge, so therefore, now not field now, but let's think about the force on this positive test charge. Well, as I just said, the force on it would be the vector sum, the superposition of the force on it for the positive charge plus the force on it for the negative charge. Then you have a strong repulsive force for the positive charge, strong because it's so close to the positive charge, and it's going to have a weakly, comparatively, weakly attractive, did I say that correctly? Positive charge, the positive test charge at this point is a strongly repelling force on the positive charge, and a weakly attracting force on the negative. And so if I add both of those together, then the force on it would point like this. That's the net force from the positive plus the negative. And as I was just saying, by definition, therefore, the electric field of this dipole at this point also points in this direction. Why? Because I imagine a positive test charge at this location. And let me rewrite that. If I chose a different point, say down here, and once again, imagine putting a positive test charge at this point. Again, let's think about the force, the net electric force on such a positive test charge here. If I did, then it would experience a strong repulsive force from the positive charge. This is the force from the positive charge. It would experience a weak attractive force from the negative charge. And so the net force on here, I did this in the previous lecture, put this vector down here. Draw the vector sum. That's the net force extracting. And so at this location, then the net force on a positive charge placed at that location points this way. If I were to use another point, at the same distance above the positive charge, at this point you should pause the recording and do this same analysis that I just did for this point. In other words, draw the positive force vector, draw the negative force vector, and then draw their vector sum. Pause the recording now and do that. Good, you got it. I know you paused. I know you did. I have every confidence because plus I can see you. All right. Strongly repulsive force. So if you imagine a positive charge placed in this location, strongly repelling positive force there, a weakly attracting force there, again, putting tail to tail. And draw the angle. There. I'm having a brain fart. That's all right. It happens. I'm sorry. Drawing like this, drawing the tail to tail, and then move it so up here to the tip tail. Can you imagine? I'm recording this. important that when you move the vector in your diagram, you don't change either its magnitude or its direction. The mistake that I was just making, and that I kept correcting, was that when I moved my vector up here, I was instinctively trying to point it directly at the minus sign, but I want it to point, the minus charge. I need to keep it pointing the same direction. Because I'm not evaluating the vector field at this location, I'm evaluating the vector field at the vector force at this position. So okay. And so then now you draw the resultant vector going from the tail of the first vector to the head of the second vector. And that's the net force there. Okay. And my magnitudes are not quite the same. These two should really be the same magnitude. That's because I was just sort of hand waving, guessing the lengths of the arrows here. But the direction is fine. Okay, and I'll just do a couple more, I think, maybe 3 more. Like that. If I were to look at this point here, now a positive charge placed at that location would be only weakly repelled from the positive charge, but it would be strongly attracted to the negative charge, and so the vector sum like that. Down here, directly below the negative charge, I'm going to have a force of weakly repelling. I'm going to have a force that's strongly attracting. And I will therefore have a net force at this location that looks like that. Okay. And like I said, finally, I'll just do one more. At this point here, I would have again, if I put a positive test charge right there, it would be weakly repelled by the positive charge, weakly because it's so far away from it. It would be very strongly attracted to the negative charge. And so, and it's probably here I think the later point that the net force is going to point to that, and we would stop that magnitude. And now finally, let's see this thing. The other side. The same distance on the other side. The positive charge placed here will be strongly repelled by the positive charge and only weakly attracted to the negative charge for a net force and field, net force anyway. That, okay. I think I've labored the point long enough. What I have done here is drawn a few representative samples of electric force vectors. by definition, the direction that these force vectors point, since I chose to use a positive test charge in my analysis, then by our definition of the direction of the electric field, the direction that these forces point, the electric field at each of these points must also point in the direction. Okay? So I can, instead of interpreting all these as electric force vectors, I can equally well interpret them as electric field vectors. Okay, and so I can say that every one of these, at this point, the electric field has this magnitude in this direction. At this point, it has this magnitude in this direction, this magnitude, direction, this one, and so there's that. Now, I could, if I wanted to, draw lots and lots of these things, and I'd have a paper full of vectors. Every one of them representing the electric field at a different location in space. Remember, that's what a field is. A field is a physical phenomenon who has whose value depends on position, and since this particular field is made up of a vector quantity, this is a vector field, and therefore, at each point in space, the electric field vector has a different magnitude and a different direction. And so as you can see here. Yes. Now, the problem with this approach, of course, is that this is very, very tedious. And it is for this reason that we invented the idea. The reason I had nothing to do with the invention of this idea is there's something with the liability of not having been born. It is, from the early 1800s, Michael Faraday, English physicist Michael Faraday, first came up with this idea of a field and a field diagram. And so what the field diagram does is it replaces all of these vectors with the diagrams that we've seen before. And frankly, the field is just easier to understand, easier to picture. And of course, you've seen it before, and I'll go ahead and draw in. The electric field diagram has an effect of forces. Whoops. I think we like this. And I'm moving my field vector for a reason that is unclear in a moment. I'm just shifting into cover for a second. Okay, so there we are. As I say, the purpose of the field diagram is to simplify the process of picturing the field, because a paper full of vectors is not particularly informative, but a field diagram is a little easier to record. Okay. So, having done this, what I can do now is make the connection between the vectors and the field, and second of all, that will move automatically into the rules that you have to follow, the rules that you have to obey when you are constructing an electric field diagram. Vectors are pretty easy. We're good with vectors, but what about the field diagrams? So, now that I've set you up for it, from the connection between field vectors and field lines, in the next tutorial, we'll take that next step, which I said we would do this recording, but takes the amount of time that it takes. Okay, next recording, please.